Alright, let's go over some code. So, some people are talking about me plagiarizing when I copy and paste code for my program. So, let me make sure my mic is up. And we are up and running. Okay, so, first of all, let's look at the design of my program. So, I have a few elements here. So start and stop buttons. What the start button does is it will create a 512 by 512 pixel rectangle, a pseudo monitor, if you will, for the virtual processor here to draw pixels onto based on random pseudo processor code. We'll go over the design of the pseudo processor here in a minute, but we're going to go over the main structure and flow of our program here. Now, I'm not going to claim to be some super master elite coder, but did I write this code? Absolutely. Okay, so we got start and stop button. Stop button, it's more of a pause button. It enables and disables both of these timers here. It'll disable the timer. So the whole purpose of pausing would be if you want to just like save a particular graphic state, you want to stop the program from drawing and from running. It'll stop iterating, cycling through the virtual processor code. This ticks thing here, this is more of a debugging thing. This is basically getting the timing of a single cycle of my virtual processor. And I kind of use it just to try to optimize how I structure my code. Actually, this runs through all of the code at once, and then once the code overflow flag triggers, it'll show the number of ticks it took. So now that we know the design, let's go over some of the basic stuff. So this is, I mean, some people don't like so many kind of global things, static variables, public variables, which these aren't really public, this is a partial class, but you know, this is generally how I kind of structure my programs. I've written probably dozens of AIs, hundreds of programs. Some things I just play around with, but I've written a lot of fully functioning programs. I can even show some of those someday, but for now we're just going to focus on this. So here's our graphics variables. Some of these are obsolete. So this is for this is a link to the form graphics here. You use the create graphics function that allows us to draw the rectangle onto the form. The bitmap graphics is just drawing to the bitmap rectangle that gets drawn to the form. I used to have a back buffer. I don't use it anymore. In fact, I might as well just go ahead and delete this right here. And here's the back buffer here. And as you can see, here's bitmaps that we're storing all of our stuff in. We got the inherit flag and the failure flag. This is basically thrown into the program loop whenever these ring true. The inherit flag will run a mutation algorithm. We'll look at that in the virtual processor, and it'll mutate some of the virtual code based on the state of the failure flag. If the failure flag is true, then it will mutate. If the failure flag is true, then it will revert to the previous code, and then it will mutate new code. If the failure flag is false, it will save the current code to be what's reverted to in the future, because this will run about as often as our timer.tick2, um, our second timer there. Our second timer, I never really mentioned the timers. Let me just go through these real quick. So the first timer is just, in general, how often we're going to draw the bitmap to the screen. So right now I have this set at 100, which means this will run 10 times per second. So it's basically 10 frames per second locked. But if I want to do 60 frames per second, then I'd change this to 17. And I don't do 60 frames per second because there's a lot to be desired in performance, because we're running a processor on top of a processor, so there's a lot of performance issues with that. And I'm running this on a form. I'm not running any off of my graphics hardware, so that's another thing. And our second timer determines how often the fitness function runs on my virtual processor. And we're going to go over in general what that does. But I just want to make sure I can explain this code so that any idiot who thinks I'm plagiarizing knows that I fully understand my program here. And of course, the reset flag will basically just reset everything to its initial conditions, create a new bitmap for everything. It just basically resets the whole program. And the tick label is just, it's just more of a public link to this, so I can access it from the virtual processor. That's why I have it named here. And of course, I define it down here. So we got our tick label here, label 1. So yeah, there's that. And then we have a queue here. And this queue, it works in my fitness function down below. We'll go over that here pretty quick. But it basically counts the number of pixels. And, oh no, this queue will take the number of pixels in the current image, save, and then it'll corrupt. And then what this is for is you have a number of images that you save the number of pixels to. And then what we're trying to do with the fitness function is have the failure flag be based on if the number of pixels in the current image is higher than the number of pixels in whatever rank you want to test against. So for example, if you wanted to test if it's better than just the median, you would take this, convert it to an array, and you would take the median of that array, and we'll go over that in more detail. So here's our initialization. I already went over this. Here's our put pixel function. This is kind of obsolete. I don't use this anymore. I just go direct off of the image. We save the image to the virtual processor. Delete pixel. It just sets the color to. It just basically sets the color. Yeah, it sets the color to black, of course. And the X and Y is the location of that. And this is kind of where our main loop runs. And it's a little bit weird. I don't have this set aside into a separate function. I could do that, but I haven't really seen a reason to refactor my program that way, so I haven't done it. But yeah, this is our program loop. So what happens here is if the timer's running and for some reason like the button gets pressed, it's just like, don't worry about it, and it just prevents us from running multiple iterations of our near infinite loop below. So we enable the timer, because if the timer's false, then this will pass, and then we initialize our drawing thing. So we set the color to completely opaque, and then 111, and that's RGB, and then we set it, here's the rectangle from 0 pixel to 0 pixel, and then 512 to 512. And we're just setting that to the bitmap, and then we draw the bitmap down there, but we'll go into that. And then we define our virtual processor here, and then we send it our bitmap that it'll be drawing to. This I equals 0 here, this is another obsolete. This is more of a frame counter for infinite loops, but don't need that anymore. So of course our application do events, that just allows the form to calculate events during an infinite loop. So it just runs that, and then it'll like paint to the form and do all the things, do all your on-click events, all that. And then like if our reset flag is that we talked about up there, if that's set, then we're just going to refill the rectangle, and then we're going to define a new image here based on the drawn image, based on what this is drawing to it. And so we're basically just resetting the whole processor to its ground state. And then if the inherit flag is set, again, it will reset the status of that, and then it will we run our mutation, which is called combine, in our virtual processor, and then we send it the failure flag state, and then we initialize the flags. That's the way I go about it. Doesn't look the cleanest, but that's just how I write it. Pay me if you want me to write it different, I don't care. And then we run our virtual code right here. So this is make sure whenever we resize the form, we're always going to show the full bitmap as much as we can, because if you don't do that, then what happens is if you maximize, it won't redraw. So although I think the update algorithm actually takes care of that, I don't think this is needed, but I don't see any reason to remove this code, so if the code's not broken, don't remove it. And this is our stop button right here, so it just inverts both of the timers, and this draws every time. This is our FPS lock here, so it'll draw every time that the timer goes off, and then it'll call for the form to update its graphics, so that we actually get to see the image, the refreshed image. And this is this is something I didn't talk about, but it's actually good to bring it up here. This is just when we press the space bar, we enable and disable the mutation algorithm. So once we start the form here, I don't think it'll do me much good, but once we start it, it won't immediately run the mutation, so you gotta press it. And this is really useful for example, if you see a pattern that you like and you want it to continue, the AI to continue the pattern, then what you do is you push space, and then it won't run the mutation algorithm on it anymore. It won't keep resetting, because typically you want to have your second timer there set to a short time so that it can learn and branch. And here's our mutation timer. So what happens is every time this ticks, like, we get inherent flag equals true, which means we're going to run the mutation algorithm the next time that the infinite loop is run, because that's going to ring true. And then what's going to happen is this is the pixel count right here, the cur count. and then we just have it iterate over the height and the width of the bitmap. And then what we do is the way we detect fitness is any time that a pixel is redrawn doesn't equal the base color, which is again fully opaque, and then 111 RGB, we increment the pixel count, and then we store the pixel count in our queue because we want to test it and see where it fits in to our like what percentile or whatever tile it fits in. And then what this does is this kind of caps our queue. I don't know if there's a better way. I've tried to find ways to like limit queues without having to write functions for it, but this is the way I do it. So what it is if the queue gets over 2,000 long, what we do is we pop out the front. So basically, the most distant in the past entry is what we do. And then what we do is we define our sorted queue, and then we convert this into an array, and then we sort it. And this is how we get to what we can test. And oh, okay, yeah, this is how we define it. So basically, the way we're defining this is the 95th percentile. So if it's not in the 95th percentile, then we set the failure flag to true. In other words, it'll just keep reverting until we get something very high. Now, I've tried different values for this. I've tried 1 over E. I've tried lots of different things. I've tried 4 over 5, 1 over 2, etc. This one seems to work pretty well. And there's additions I need to do too to the general way I'm doing things. So just brief go over. This is how I was going to store my opcodes, but I decided against it because I think it just looks better if it's all neatly in one class here. So anyhow, here's our virtual processor. Here's our global random variable. These two variables are kind of depreciated. I don't use them. But this is basically the success and failure mutation rates. We'll go over mutation rate once we get to the mutation function. Here's our registers. Here's our X register, Y register, A register. Now just kind of a brief intro to assembly. Your X and Y registers will usually index off of specific addresses. And so what you can have is a loop that iterates until X is equal to a certain number, and have it do a process so many times. So there'll be a lot of closed loops like that. The same thing with the Y register. And we'll kind of go over indirection and indexing once we get down below. A is our accumulator. The init values are used for our mutations because X, Y, and A can change. And we want to have initial values for X, Y, and A because that'll produce different results. PC is our program counter. That's basically what point we are in the virtual instruction set. And then SP is the stack pointer. That's the point in our virtual stack that we're in. And I want to do a virtual stack because I can do a rolling stack and I won't get any errors. Here's our placeholder. This shows green underline, which means not being used, but it's actually useful because I could send references to local variables. and that's very helpful instead of writing another addressing function that does values instead of references. It's nice to have the ability to just send values, and that's kind of a roundabout way of doing it. Transformations is the number of mutations that have been run. It's more of a debugging tool than anything, because it doesn't show up anywhere, but it's there. Our bit depth is the maximum value that any of our figures can hold, so once we get to the RAM and stuff and the stack, you'll get to see kind of what that means. Right now we have it just set to the maximum integer value, because it's the easiest way to store bits for color. So we have the running flag here. I think I used that. Yeah, I can't remember where I used that, but we'll go over it. And here is where I would do my ticks that I would show on the forum. Right now I don't really use it, but I just keep it there in case I want to do tick counters to see how long my functions take. And here's my processor flags. I've only got 3, but a normal processor would have usually 5 to 8 bytes used. But I only use 3 because I don't see a point in having a stack overflow or a carry flag or what have you, because I use integers and I use unsigned longs, so there's that. Here's our memory. Here's a virtual RAM, 256, not really bytes, but 256, I guess, commands long. And here's our init RAM. This is just the initial values for our mutations. Here's our virtual stack. Here's our instruction set, and here's the initial for the program. I don't really feel a need to have an initial virtual stack because, you know, I don't think everything needs to just be randomized for it to be useful. Like, sometimes you kind of want everything to be zeroed out so that if it's jumping the subroutines or whatever, like, you kind of want it to be able to go back if it can, but that's kind of useless too because I got rid of a lot of the jumping mechanics. I got branching, but I don't got jumping, and we'll go over that. And here is the start of my tiling. I'm not even close to done with that. I gotta change how everything draws, and here's my to-do to do the tile system. And so, briefly, you know, I can go over that real quick. Let's kind of run my program too. Let's just kind of get a little bit of a feel for it. I hope I'm not going to get an error here because I have edited some stuff. So we'll wait for this to run. If it'll ever run. I got it in debug. So when I click start here, here's our square. Now, as you can see, it was black and then it turned white. So what I could do, if I hit spacebar, it'll run this so many times. And actually, this is kind of useful because it'll run about half the time. And so what this will do is, after every iteration here, I don't want to give anyone epilepsy, but you might start to see something different. But this is pre-programmed code, and I'm kind of going to go over that here in a second, because it's written in a virtual assembly. So we're not going to go wait on this too long. No. So if I hit stop here, it'll pause that, and then this will, I guess it won't iterate again, will it? That's weird. So yeah, some of this stuff I didn't test, but the point I'm trying to make is the way it's drawing now. is 1 pixel at a time. What I want to have it do is, instead of having my virtual processor reference pixels, I want it to reference tiles. And then I want the tiles to be placed on a grid. Instead of the 512 by 512, we'll do 512 divided by 32, and then 512 divided by 32 in a grid. And then what we'll do is, like, we'll be able to edit tiles, and not only that, but we can actually program operations within the tile. For example, if we want to bit shift all the pixels in the tile one direction, if we want to do some rolling commands, there's a lot of different things you can do with tiles, and it's faster because I don't have to wait 2 seconds for the screen to fill. It'll fill almost instantly. In fact, it'll be almost 1,000 times faster with a tile system. It may not produce the kinds of patterns, but you could also get, like, emergent, intricate kind of things, if you know what I mean. So I'm going to close this for now. We may open it back up soon, but I just wanted to explain this the best I can. Okay, so what this is, we got corruption list, RAM corruption. So what these variables do, it's the corruption list is the list of both addresses and values of the instruction set, the initial instruction set. And what happens is, when we revert, when the failure flag is true that we were talking about from the form, it will use the corruption list to revert back to the original code before it corrupts new stuff, so that we're branching off of the old that we liked better than the new. And then RAM corruption does the same thing, but it does it with the virtual RAM, the initial virtual RAM. And then X, Y, and A revert is the same thing. It just, when we need to revert, we just set the initial X, Y, and Z back to its original. And then we have a copy of the bitmap from the form we were talking about over here. This just allows us to edit all of our pixels from here. Here's our constructor, our virtual processor, and it of course takes the bitmap from the form, and then it sets that here. And then what this does, both these for loops, they will assign a random value to the virtual processor, the virtual instruction set, based upon, hold on, oh, looky what I found. I found a little bit of a bug. Okay, this is a problem, because we want to set, there we go. See, you can even find bugs here. I got this all lowercase for some reason. There we go. Okay, so perfect. I found a bug. It doesn't make a huge difference because our instruction sets aren't that big, but it does matter, especially for certain things. Interesting. But anyhow, this will set a random value for the instruction set based upon the bit depth, which we defined up here as our int.max value, but it'll constrain it to whatever we want to set it to. So this just basically sets our random opcodes, and we'll go over the opcodes in a second. The initial RAM kind of the same thing, but the RAM will be more of reading to and writing from. You won't be executing many instructions from RAM. I thought about being able to do this, but I just think that if we do our instructions from ROM, and then we just, it's not really ROM, but you would typically call it program ROM if you're talking about emulation. But that's another thing. Of course, this sets our initial X, Y, and A, our accumulator and our XY registers. And then we just set the reverts to the initial, just so that if we don't like what we see in the initial steps, we can always revert back. And then this is more test code. What this does is that writes all the white pixels to the screen. So basically these are commands. And the way the commands are is simple. So anything from 0 to 100, those are instructions that will directly write pixels to the screen. So basically we're taking a position and then we're doing a color. And then what happens is, like we're defining, like RAM direct is opcode number 5. And what RAM direct means is you take the next instruction's RAM address, which is 0 in this case, and then you write that value to it. So we're writing whatever is in the next instruction. So we're writing 0, the value of RAM 0, to the screen. We're writing to that location, rather, I should say. Yeah. That's basically what we're doing. Okay, so, and this is doing the same thing, but to address 1. And this is for the color. So we're doing the location, which is in RAM address 0, and then we're doing the color, to which is in RAM address 1. And this is why I have int.max value, because if it gives us enough bits where we can end that. Like, we only need 24 bits, but just being able to use the entire integer range is just better than having to divvy up between 24 bits of the int as opposed to the full 32 bits. And then here are the actual instructions. This does not write to the screen, but it'll write to read to and write from various instructions. So opcode number 16 is increment. And so what are we incrementing? We're incrementing RAM direct. And what's RAM direct again? We're just taking the next instruction's RAM address. So we are incrementing RAM address 0. And then we end. And then this end is important, because what this end will do is it'll revert the program counter to 100, and then it'll start the write routine here. And we'll go over the whole loop within the processor itself, the full cycling. And so when this ends, it'll go through this code again, and then it'll execute this code again. So what you're going to do here is we have our virtual ROM address set to 0. Okay, when this runs, it'll increment by 1. So it'll be 1, it'll be 2, and we're writing a white pixel every time. And so when we drill the rectangle here, like, it initializes as black, but it's just going to go from left to right, drawing white pixels, and then once it gets to the 512, then it's going to go to the next line, right? So there's that. And then we have reset, which is just our initialization. It initializes everything mostly for our mutation, because we don't want to run the constructor every time, so we're just going to run the reset. So we set our program counter to 100, we set our stack pointer to 0, we clear out, we set everything else to their initial values, X, Y, and accumulator. We run through our RAM, and then we set everything back to the initial. So we just want to run everything clean again. And remember, we're also setting the bitmap to black. Okay, the virtual stack, we zero out everything. And so we're just starting neutral. And then we set our instructions to their initial values again. The combine, here's where the running flag is. So basically, all this says is, like, if you're running, we don't want multiple combine functions to be running concurrently, because the ticks are on separate threads. So, just in case we have multiple calls to this function while another one's still running, we don't want that. So we want to make sure anytime it's called again, for whatever reason, we're just leaving. Okay, transformation. This just is a counter to how many times we've run the mutation. Here's our mutation rate. And basically we just look at if random values are beneath this point. And then, of course, if the fail flag is true, which is sent from the form function we're calling combine, we're just reverting everything back to its previous self. And then we just set the reverts to the initial values. And this is for, if the fail flag is false, then we want the new revert flags to be the current values, because we had a positive result. And this isn't the best learning. This isn't even neural networks Q-learning. This is very, very basic machine learning. But I actually find it's pretty effective at this, at least from the limited amount of processing time it's given. So here's our mutations. We first start mutating our instructions, and so basically we look at the mutation rate. We simply check. This is interesting. Yeah, I don't think this is what I want, and in fact it's not what we want. See, there's another little bug. Because what I was doing, I was like, just before I tried to go to tiling, I tried to find a mathematical way where I could do this without looping. And I know there's a mathematical way with probabilities, but there is a problem with me in advanced math. Sometimes we butt heads, and I'm not particularly great with advanced math, so sometimes I have to do things in like a less optimal way. Like, it's not hurting things much, because we're only running this maybe every second, and even with running this loop a few thousand times, so it's going to take like a couple milliseconds. But yeah, I can't figure out the way to do concurrent probabilities in a way where I can get the number of occurrences, or like the average number of occurrences, or I could simulate running this loop 2048 times. But yeah, this is how I have it. Like, we just run through, we test each of the instructions against the mutation, and if the mutation is, if it's less than the mutation rate, then we mutate the whole thing. Um, and we have a do while here, which we basically run this until we get something that's not contained within the dictionary. This just prevents us from doing duplicate corruptions, and it's a lot easier to do this with dictionaries. And yeah, of course, we're just we're setting it to random based on that. If we're below, I think I'm doing this right. Well, I'm beginning to wonder if this one's a bug too. Because why am I mutating this every time? Huh. Okay, well, I'll have to look at that at least. Because, yeah, I've rearranged, I've changed all this code, and yeah, but the same thing for the initial RAM, and then we run the mutation against the initial X, Y, and accumulator, and then we initialize, and then we set the running flag to false so that this can run again. So advanced just means we're going to return a value from the instruction set, and then we're going to tick the processor one cycle, and then we're going to return that value. And then the tick just means we're incrementing the program counter by a certain amount, and if it's above the buffer that we give it, which is 100, then we set the overflow flag, and then once we have the overflow flag, then we run the draw out. We run the drawing code, and then we reset the PC to 100 again. Pop just runs on our virtual stack. It just returns the value, and it decrements the stack pointer. And push is the opposite. It shoves a value given here to this stack, and then it increments the stack pointer. And then get RAM, it just let's see. That's actually interesting. I don't have. Okay, this should have. This is interesting. Okay, so I need to be running this code on it more than anything. Okay, yeah, because if we're getting RAM, getting RAM and getting ROM, then we need to be running this code. So we're just going to go. Yeah, that's true. We need to be comparing the RAM and the ROM too. There's no reason not to be setting our flags here. So let's kind of go over these flags anyhow. As I set these, here's some live programming. For my plagiarized code, according to somebody else. So we have the address. We test the address against the bit depth divided by 2. So in other words, we're checking if the sign bit is set or not. If the sign bit's set, then we set the negative flag. And then same thing, if it's 0, we set the 0 flag. And then those will be important for opcodes later. Same thing for ROM, it just gets a ROM address, or it gets a RAM address. And so here's our X and Y's. We don't need to really do Um, I might or might. I don't think I need to do any flags with those because I've kind of went through this before. I don't know why I never set the flags for RAM and ROM. That's interesting, especially for the getting. Okay, let's move on. All right, so this is just setting um, the value of a register. And I don't know why I don't have this set as a reference. Huh. That is interesting. I think just because... oh, I think I kind of get it. Okay. But anyhow, here's the fun part. Here's our opcode list. And I don't know how helpful it's going to be for me to go over the opcodes, because explaining this to somebody who's never even looked at processing code, it's going to be like Greek. But I can go over it briefly just to kind of show at least that I know what I'm talking about. So what we do is we get the total opcode, set it as our command, and then we find the reference to our operand here. We call our find reference. So this is just basically getting the value we're going to be operating with here. So for example, for load A, or LDA for short, we're just going to set A to whatever this is, and then we're going to check it against 0. Why we don't check it against negative, I don't know, but we don't. Oh, I know why we never did that, because we had our bit depth set differently, and I didn't want to have irregularities with the branching. But yeah, we set our 0 flag if A is equal to 0. And then store A just means we store whatever value's in A into the operand here. So for example, if the find reference sends back Y, then we'll set the operand to Y. We'll set Y equal to the accumulator. So compare A just means we are looking to see if A is negative or A is 0, right? So basically, then we're comparing X and then we're comparing Y the same way. Reset just resets the 0 and negative flags. And here's the branching. The branching just says if the negative flag is set or if it's clear, or if the 0 flag is set or clear, then we will branch forward up to 64 bytes, or 64 commands, I should say, not bytes. Self-explanatory, we just add, we just do set register here, we just add that, and then it'll set any of the 0 or negative flags, or it'll wrap it around. Same thing for subtract, and just means when we're talking about bitwise and, it's really hard to explain. The only thing I could say is there's no way I can really explain it, but for the and or NAND or XOR, You're going to have to look up bitwise operations because there's no way I could really explain it without writing it down on a piece of paper. But this basically will AND all of the bits between A and the operand. This one will OR all the bits. ORing is also another way of combining. ANDing is almost a form of subtraction almost. Not really, though. No, that's a bad way of putting it. But, of course, NAND will take the AND and then take the NOT of the AND. So, in other words, not AND as in NAND. And then XOR, or exclusive OR. If the bits are the same, it sets it to 0. If the bits are different, it sets it to 1. And it goes through all the bits of A in the operand, and it'll very interesting stuff there. So increment, it just takes the operand, and then it'll increment it by 1, whatever that result is. And load X just means it's the same thing as A, but we're just loading the value of X into, from whatever was there. And then we're loading Y. Then store X, store Y works the same way. Dividing by 2 and multiplying by 2. This is just so that we're basically shifting left and shifting right. In fact, I should just do it that way. But, at the time I just did it this way, so that's just, here's the NOT operation. I have that separate just because I added that later. So we're just taking the opposite of the bits of the accumulator. I really should that's interesting. I couldn't do that with that. I'm trying to think on the fly here when I'm trying to explain this at the same time. But yeah, always looking for improvements in my programs. The program I didn't write, by the way. So there's to you. Don't even know if your name's worth saying. Okay. So decrement just works the opposite of increment. It just subtracts 1 from the operand. Then we have push. It's basically the only way we can push something onto the stack. Then we have no operation, and then we have end. And no operation's more, it's like almost a way for the program to kind of delete a command, I guess, because it does nothing, and that's the whole point. And then this is basically ends the program. We just set the PC overflow flag, and then we let we set the PC back to 100, and then we write to the screen on that frame. Alright. Oh, and here's a bigger one right here. Okay. Address modes. How am I going to explain that one to a layman? Alright, let's try this. Okay. So, rec count. This is our recursive counter that we have up here. And then what this does is, if we're doing any kind of indirection, it keeps count of how many times we're running it. And then if we get to level 5 indirection, or like a 5-way pointer, some would call it, we just return the next command, and then it'll return everything else through recursion. Okay, so case 0, immediate. It just means the operand is just whatever the next processor command is, so we just return that. And of course we return A, X, and Y. They could both be read from and written to based on it, which is convenient. It helps I don't have to write two functions for this. So we're going to skip here. RAM direct just means we are getting the address from RAM based on the next processor instruction. So we're just going to get that. And then direct X means, or direct Y means we're going to take the next instruction and then we're going to add Y to it, and then that's where the address of RAM we're going to use. And then we have indirect. Indirect will get the address of the next ROM address, and I'm never going to be able to explain that one to people. But basically what this does is it will take the next processor instruction, it'll run it through here. So we're going to run this function recursively. And so, for example, if we get 1, we're just going to get the RAM address of whatever address the accumulator points to. So, for example, if the accumulator is 1, then the RAM address we will get is whatever RAM address 1 is, and then that'll be the RAM address we use here. And this can go 5 layers deep. And indirect Y means we do the indirect and then we index. So, for example, if the accumulator is 1, we're getting whatever, and let's just say the accumulator is 1 and Y is 5. So we get whatever the address is of 1 plus 5. So we're getting RAM address 6, and then we're using that, the value at RAM address 6 to decide which RAM address we're going to directly read from, that we're going to send as the operand. And then indirect X, we do a little bit differently. Now, I don't know how all processors do this, but I refer to the 65 series because that's what I corrupt in my ROM corruptors. So, what the Motorola 65 series does, 6506, 65C816, is your indirection on Y, you indirect and then you index. And so I explained Y wrong. Okay, so I'm just going to explain X. So you indirect and then you index. So if you're indirected to address 1 and then you're indexed by Y, that's going to get you to RAM address 6. But if you indirect index by X, you are doing the indirection and then you're indexing the indirection. So instead of basing it on whatever get RAM 1 is and then indexing that by 5, you're getting whatever RAM address 6 is and indexing, and then you're indexing it by 5. And it's like I said, I'll never be able to explain that in the way you guys are understanding it. But my point is to explain that I understand this code perfectly, and it's not to really teach you guys how to do basic processor instructions. So the ROM indirections, same thing. We're just dealing with processor instructions. There's no way I could even tell you how that's interesting, so I'll just leave it at that. ROM is the same as RAM in this case. The only thing is you're not running instructions on RAM. at least here. On other processors you can, but that's not the way this is. This is pretty much where RAM and ROM will always be separate. So you change your instructions when you're editing ROM. RAM, you're just reading from different addresses. And then you have the stack where you just pull from the virtual stack. And then you decrement the stack counter. And then I just have reference A here because my compiler bitches if I don't give it a return, at least a case default return value, but I just decided let's return reference A, even in the case it somehow gets through our switch statement here. And then here's run. Now, not a whole lot to explain about this one, but basically we're just getting the next processor instruction, we're executing the opcode, and then after we execute the opcode, if the PC over flag is true, which is either if it's overrun the buffer, which is the length minus 100, or if there's an end command, which is command number 27. So if it encounters either one of those, the PC overflow flag will trip. Then the first thing we do is, of course, we reinitialize this. This should probably be at the bottom, but, you know, I'm a newbie programmer. So what we do is we set the PC to 0 temporarily, just so that we could run the draw code. And then we define all of our operations here. So raw 1 and raw 2, this defines, raw 1 is what our position will be, and raw 2 is what our color will be. So we're taking the first, so for what our position will be, we're taking the first 9 bits of raw 1, and then we're combining it with the next 9 bits of raw 2. And that will get our total position, the XY position. We're running this from one integer too, so. And then 3, 4, and 5 operations will run on raw 2. Raw 2 is our color. And then we're, of course, doing the first 8 bits will be red, the second 8 bits will be green, the third 8 bits will be blue, and that's what gets us our colors. Then we set the pixel value to that color, which we're going to have to probably do tiles. But for now we're doing pixels. This will be changed. And then we set the PC to 100. And then I have 2 things commented out. These are just editing our ticks in case we ever want to calculate ticks. But it's pretty, you know, it's not that kind of expensive operation. This is something I want running like every time this runs. So I just let that run, and then after 100, then it goes back through here. After the infinite loop here runs, and then there it is. So there's, I guess, the program that I supposedly never wrote, fully explained, fully scrolled through. So, you know, I hope you learned a thing or two. Most of you watching probably different because, you know, let's face it, those who talk shit can't program their way out of a wet paper bag, I guess. Kind of a bad analogy, but hope you enjoyed.